Walk into Rome today, and you'll find a building that has absolutely no right to still be standing. The Pantheon, built in 125 AD under Emperor Hadrian. No steel rebar, no modern Portland cement, no computer-calculated load distribution. Just stone, volcanic ash, and the engineering will of a civilization we casually call ancient. And yet, it stands perfectly. 2,000 years later, its unreinforced concrete dome remains the largest of its kind in the entire world. The oculus at its crown still opens to the sky. The walls haven't cracked. The foundation hasn't shifted. Tourists walk through it daily, and it holds them without complaint, just as it held Romans, medieval pilgrims, and Renaissance artists before them. It is not a ruin. It is not a restoration. It is the original structure, breathing in real time. Now look at what we build today. Modern concrete, the stuff holding up your apartment building, your office, your city's infrastructure, has a rated lifespan of 50 to 100 years. Engineers know this. City planners budget for it. Governments quietly set aside funds for the inevitable crumbling. The concrete beneath your feet is already dying, slowly, invisibly, but on a timer. Roman concrete. Scientists who drilled core samples from ancient Roman harbor walls, structures submerged in seawater for 2,000 years, found something that defied explanation. The concrete wasn't degrading, it was getting stronger. Seawater had triggered a slow mineral growth process within the mixture, reinforcing it from the inside out over centuries. The Romans had, accidentally or intentionally, created a self-healing building material that modern chemistry is only beginning to understand. The gap isn't a minor technical footnote. It's a chasm, a 2,000-year chasm. Here's where the story stops being about archaeology and starts being about something far more uncomfortable. This is not a case of lost technology. The research exists. The papers have been published. The chemical composition of Roman concrete, its use of pozzolana, volcanic ash, seawater, and lime clasts, has been analyzed, documented, and peer-reviewed in journals like American Mineralogist and Science Advances. The knowledge is not missing. It has been systematically set aside. In laboratories, yes. Researchers study it with fascination. But in construction policy, in building codes, in the materials your contractor orders for your home, the Roman formula is essentially nowhere. The transition from "we understand this" to "we use this" has never happened. And the silence around why is deafening. Because here's the question nobody in the construction industry wants you to ask. Who benefits when buildings don't last? Think about it structurally, not emotionally, structurally. An industry built on repair contracts, renovation cycles, demolition permits, and new construction bids does not profit from permanence. A building that stands for 2,000 years is a building that never needs to be rebuilt. A building that cracks in 60 years, that's a revenue stream. The modern construction industry, worth over $13 trillion globally, is quietly dependent on the predictable, scheduled failure of its own product. Planned obsolescence isn't just a smartphone strategy. It's poured into your walls, cured at room temperature, and sold to you as up to code. The Pantheon isn't just an architectural wonder, it's an indictment. And somebody, somewhere, decided you weren't supposed to notice. While Augustus Caesar was busy reshaping the Roman Republic into an empire, a relatively quiet military engineer was doing something that would outlast every emperor, every conquest, and every political border Rome ever drew. His name was Marcus Vitruvius Pollio, not a general, not a senator, a builder, a man who spent his life obsessing over the precise relationship between human hands and lasting structures. And in 27 BC, he compiled everything he knew, every material, every proportion, every hard-won construction secret, into a single extraordinary work, De Architectura, 10 volumes, the world's oldest surviving treatise on architecture and engineering. For centuries after Rome fell, this book was lost, buried in monastery libraries, copied by monks who didn't fully understand what they were preserving. When Renaissance architects rediscovered it in the 15th century, it didn't just influence their buildings, it rewrote their entire understanding of what building could be. But here's what most history classes quietly skip over. The most important chapter in De Architectura isn't about columns or temples or symmetry. It's about dirt. Specifically, it's about a gray, unremarkable powder that Vitruvius called pulvis Putiolanus, the dust of Puteoli, a coastal town near Naples that sat in the shadow of Mount Vesuvius. We know it today as pozzolana. To the untrained eye, it looked like ash, because that's exactly what it was. Volcanic ash, deposited over millennia by Vesuvius's slow geological breathing. The Romans collected it by the shipload, and when Vitruvius described its properties, he wrote with the quiet confidence of someone who had watched it do something impossible. Mix this ash with lime and water, he explained, and you get a material that hardens even underwater. Not despite water, in water, because of water. This wasn't alchemy, it was chemistry that the Romans understood empirically. through observation and repetition centuries before the periodic table existed. The volcanic ash contained high concentrations of silica and alumina. When combined with calcium-rich lime, these compounds triggered a slow chemical reaction called a pozzolanic reaction, forming an interlocking mineral structure denser and more resilient than almost anything nature produces on its own. Vitruvius didn't have the molecular language to explain why it worked, but he knew with absolute certainty that it did, and Rome was built on that certainty. Here is where the story moves from impressive to genuinely bewildering. Roman engineers didn't just use pozzolana to build roads and temples on dry land. They took this volcanic ash mixture, combined it with lime, seawater, and large chunks of volcanic rock, packed it into wooden forms, and submerged it into the Mediterranean Sea. They built entire harbor structures this way: breakwaters, piers, underwater foundations for ports that serviced the entire Roman trade network. The port of Caesarea Maritima, built under Herod the Great, using Roman techniques around 37 BC. The ancient harbor remains of Baiae on the Phlegraean coast. Structures at Pompeiopoulos, Chersonesus, and dozens of other sites scattered across the ancient Mediterranean world. These harbors are 200 years old, and marine archaeologists can still find them, intact, load-bearing, chemically stable, on the seafloor today. Let that settle for a moment. Structures that have sat at the bottom of a saltwater sea, battered by currents, colonized by organisms, subjected to immense hydrostatic pressure for over 2 millennia. And they are still there, still structurally coherent. Still, in many cases, still recognizable as engineered surfaces rather than rubble. Modern offshore concrete structures are rated for 50 to 100 years in marine environments before significant degradation requires intervention. Roman harbor concrete has quietly exceeded that estimate by a factor of 20. This is the part that broke the assumptions of modern materials science when researchers finally looked closely enough to see it. In 2017, a team led by geochemist Marie Jackson at UC Berkeley extracted core samples from Roman harbor concrete and ran them through X-ray diffraction analysis. What they found inside those ancient walls rewrote a fundamental assumption about how concrete behaves over time. Inside the Roman mix, seawater had been slowly percolating through microscopic channels in the concrete for centuries, doing what seawater does to modern concrete, which is aggressively corrode and expand the steel reinforcement until the structure cracks apart from within. But Roman concrete has no steel. It has volcanic rock, and when seawater reached those volcanic minerals, the chemistry changed completely. The salt water was triggering the growth of interlocking crystals, specifically a rare mineral called tobermorite, directly inside the concrete matrix. These crystals were filling in the tiny fractures and voids that naturally form over time, reinforcing the structure at a microscopic level. The waves weren't wearing the harbor walls down. The waves were completing them. Every storm, every tide, every decade of seawater exposure was, counterintuitively, making the Roman concrete stronger than it was the day it was poured. The ocean itself had become a co-engineer, invited into a slow-motion construction process that the Romans had set in motion 2,000 years ago and walked away from. No modern building material behaves this way. Not one. We have materials that resist water. We have materials that tolerate salt water for a limited time. We do not have materials that recruit seawater as a structural ally across geological timescales. The Romans did, and the formula, every ingredient, every proportion, every process step, was written down by Vitruvius in 27 BC in a book that has been sitting in university libraries, translated into dozens of languages, freely available to anyone who looks it up. The secret was never truly lost. It was just inconvenient. For most of the 20th century, the durability of Roman concrete was treated as an interesting historical footnote. Admirable, perhaps mysterious, but ultimately chalked up to they built things thicker back then, or they just got lucky with their materials. That comfortable explanation collapsed in 2017. A research team led by Dr. Marie Jackson, a geologist and research engineer at the University of California, Berkeley, decided to stop speculating and start looking. They obtained core samples drilled directly from ancient Roman harbor walls, concrete that had been submerged in Mediterranean seawater for over 2,000 years, and subjected them to some of the most sophisticated materials, analysis technology available to modern science, electron microscopy, X-ray diffraction, synchrotron-based imaging. They weren't just looking at what the concrete was made of. They were looking at what it had become, at the microscopic level, after 2 millennia of continuous seawater exposure. What they found didn't just surprise them, it forced a fundamental reassessment of what concrete, as a category of material, is even capable of doing. The results were published in American Mineralogist and later expanded upon in Science Advances. The findings sent quiet tremors through the materials science community, because what the electron microscope revealed inside those ancient walls wasn't degradation, it was growth. Inside the Roman concrete samples, interlocked throughout the ancient volcanic matrix, the researchers identified something they did not expect to find in such abundance or such perfection: aluminous tobermorite. It's a rare calcium silicate hydrate mineral, a crystalline structure that forms under specific chemical conditions when aluminum-rich materials interact with calcium and water over extended periods. Materials scientists had known about tobermorite in theory. They had struggled for decades to reliably produce it in laboratory settings because it requires sustained high temperature conditions to form quickly, conditions that are expensive to recreate industrially. Inside the Roman concrete, it had formed naturally, slowly, at ambient ocean temperature, and it had formed everywhere, threading through the volcanic aggregate, reinforcing the interfacial zones between the rock chunks and the binding paste, filling in microscopic voids with an interlocking crystalline lattice that made the overall structure increasingly coherent over time. Here is what makes tobermorite exceptional as a structural mineral: its crystal shape. Unlike the relatively simple, blocky crystals that form in modern Portland cement hydration, tobermorite grows in elongated platy formations, flat, interlocking blades that knit together across surfaces like the fingers of two clasped hands. The longer they grow, the more surface area they cover. The more surface area they cover, the more load they can distribute. The more load they can distribute, the stronger the material becomes. Roman concrete didn't just resist the passage of time. It used time as a manufacturing process. Every decade of seawater contact was another production cycle for these living crystals, quietly assembling themselves inside the wall long after the Roman engineers who poured the mixture had turned to dust themselves. Now consider what happens when a crack forms. In any structure, cracking is inevitable. Thermal expansion and contraction, seismic microvibrations, differential settling. The physics of large, solid objects in dynamic environments will, over sufficient time, always produce fractures. This is not a flaw in engineering. It is a fact of materials science. The question is not whether cracks will form, but what happens to them when they do. In Roman marine concrete, the answer is almost biological in its elegance. When a crack propagates through the structure and breaches the outer surface, seawater enters the fracture channel. The seawater, carrying dissolved calcium, silica, and the full mineral complexity of the Mediterranean, makes contact with the lime clasts and volcanic minerals exposed along the interior crack walls. The pozzolanic reaction reactivates. New tobermorite crystals begin nucleating along the fracture surfaces. They grow inward from both sides of the crack, extending their flat crystalline blades toward each other across the void. Over months and years, the crystals interlock, the gap narrows, the fracture fills. The wall heals itself, not metaphorically, not approximately. The mineral chemistry of the material, triggered by the very environmental stress that caused the damage, executes an autonomous repair process that requires no human intervention, no maintenance crew, no injected resins or patching compounds. The ocean opened the wound. The ocean closed it. Dr. Jackson's team found direct physical evidence of this process in their core samples. Healed fractures, identifiable by the distinct crystalline signature of late-stage tobermorite growth inside former crack channels. These were walls that had cracked somewhere across 20 centuries of tidal exposure and then, quietly, invisibly, repaired themselves while no one was watching. There is currently no modern building material with a documented equivalent capability at this scale and this time scale. Not one. To understand why this matters, you need to understand what happens when seawater meets the concrete holding up the modern world. Portland cement, the binder used in virtually all contemporary concrete construction globally, is chemically built around calcium silicate hydrate, a compound that performs admirably under controlled conditions. On dry land, properly cured, adequately reinforced with steel rebar, it is strong, workable, and economically efficient to produce. In seawater, it begins to die almost immediately. The chloride ions dissolved in seawater are small enough to permeate the microscopic pore structure of Portland cement paste. They migrate inward, deeper into the concrete matrix over time, until they reach the steel reinforcement embedded within. At that interface, the chlorides initiate an electrochemical corrosion reaction. The steel begins to rust. Rust occupies greater volume than the steel it replaces, roughly 3 times greater. This volumetric expansion generates enormous tensile stress from inside the concrete. Since concrete is strong in compression, but relatively weak in tension, the expanding rust exerts a kind of internal pressure that the surrounding matrix cannot accommodate. Cracks propagate outward from the reinforcement toward the surface. The cracks reach the surface. More seawater enters. Accelerated corrosion, more expansion, more cracking. Spalling, the process by which the concrete surface fractures and breaks away in sheets, begins. Structural capacity drops. Engineers schedule emergency assessments. This process has a name in the industry. It's called chloride-induced corrosion, and it is the primary degradation mechanism responsible for the premature failure of marine and coastal infrastructure worldwide. bridges, seawalls, offshore platforms, harbor piers. The American Society of Civil Engineers estimates that the cost of corrosion-related infrastructure damage in the United States alone runs to hundreds of billions of dollars annually. Globally, the figure is estimated at over $2.5 trillion per year, roughly 3.4% of global GDP, spent managing the consequences of a material that was engineered knowingly with a fundamental incompatibility with the planet's most abundant liquid. Seawater covers 71% of Earth's surface. Portland cement deteriorates on contact with it. And the Romans, without electron microscopes, without chemistry degrees, without any of the institutional infrastructure of modern materials science, engineered a concrete that thrives in seawater, that recruits it, that gets stronger because of it. The 2017 Berkeley study didn't just document an ancient curiosity, it confirmed something deeply, structurally uncomfortable, that in at least one critical dimension of materials engineering, we have spent 200 years moving backward. The living stone has been waiting at the bottom of the Mediterranean for us to notice. On October 21st, 1824, a bricklayer from Leeds, England walked into a patent office and changed the material composition of the entire modern world. His name was Joseph Aspin. The patent he filed that day was for a manufactured cement he called Portland cement, named not for any geographical origin or chemical property, but for its superficial resemblance to the limestone quarried on the Isle of Portland, a color association he apparently believed would make it sound premium, durable, prestigious. The chemistry was straightforward. Heat limestone and clay together at extremely high temperatures, grind the resulting clinker into a fine powder, and you get a binder that, when mixed with water, hardens into a workable artificial stone. Aspin wasn't the first person to experiment with hydraulic cements. Others had done similar work in the decades prior, but he was the first to patent the process, to stake a legal ownership claim over a specific manufacturing method and its resulting product. That piece of paper, that single industrial patent filed in a Leeds office on an autumn morning, became the legal and commercial foundation upon which a $400 billion global industry would eventually be constructed. And it is worth asking, before we go any further, a very simple question that almost nobody in the construction industry wants to answer directly. Why did the world need a patented cement in the first place? The Romans had already solved the problem, solved it so completely that their solutions were still physically standing in seawater after 2,000 years. Vitruvius had written down the formula. The volcanic ash was geologically available across the Mediterranean basin in parts of Italy, Greece, Turkey, and beyond. The materials were abundant, and the methodology was documented. The results were demonstrably superior to anything that came before, or, as we now know, anything that has come since. None of that required a patent, and that precisely was the problem. Here's the commercial reality that the history books present as industrial progress, but which looks considerably different when you examine its economic logic. You cannot patent volcanic ash. You cannot patent seawater. You cannot patent the pozzolanic reaction, a natural chemical process that occurs whenever the right minerals encounter the right conditions. You cannot own, license, or extract royalties from the geological deposits of Mount Vesuvius or any other volcanic formation on Earth. Nature does not respect intellectual property law. Roman concrete's formula was, in the language of modern business, fundamentally open source. The raw materials were a public good. The process was documented in a book anyone could read. The knowledge belonged to everyone, which meant it could be monetized by no one. Portland cement was different by design. Aston's manufacturing process, the specific temperatures, the specific ratios, the kiln-based clinker production, was proprietary. It required industrial equipment. It required controlled inputs that could be manufactured, standardized, and sold. It created a supply chain with identifiable choke points where capital could be inserted and profits extracted. Volcanic ash is dug from the ground in certain geological regions and used directly. Portland cement requires a manufacturing industry to exist, limestone quarrying operations, rotary kiln facilities running at 1,150 degrees Celsius, grinding mills, quality control laboratories, distribution networks, retail supply chains. Every step of that process is a business. Every business generates revenue. Every revenue stream creates a constituency of investors, executives, engineers, and laborers whose economic survival depends on the continued dominance of Portland cement as the world's primary construction binder. The Roman formula doesn't feed that ecosystem. The Roman formula starves it. Let's talk about what the construction industry actually sells. On the surface, it sells permanence, strength, stability, security. The emotional proposition of a building is that it will protect you from weather, from time, from entropy itself. That is what every construction advertisement, every architectural rendering, every engineer's assurance fundamentally promises. But the business model tells a different story. A building material that lasts 2,000 years generates one transaction. The Roman harbor at Caesarea Maritima, poured once in 37 BC, has required 0 reconstruction contracts, 0 maintenance bids, 0 emergency repair assessments, 0 demolition permits, and 0 replacement construction projects in the 2 millennia since it was built. From a commercial standpoint, the harbor wall is a catastrophic business failure, a product so good it permanently destroyed its own market. Portland cement concrete, rated for 50 to 100 years, generates an entirely different economic pattern. Within a single human lifetime, the structures built from it will require inspection, repair, partial replacement, or complete demolition and reconstruction. Coastal and marine structures degrade faster, sometimes within 20 to 30 years in aggressive salt environments. Infrastructure built in the mid-20th century is now reaching the end of its designed service life simultaneously across the developed world, creating what engineers euphemistically call a maintenance backlog and what accountants recognize as a revenue pipeline. The American Society of Civil Engineers grades U.S. infrastructure at a C-, not because American engineers are incompetent, but because the materials used to build that infrastructure were always going to fail on this timeline. The failure was not an accident. It was, in the most literal technical sense, specified. Global concrete production currently runs at approximately 4.4 billion tons per year. The global cement market is valued at over $400 billion annually and is projected to grow. Not because the world's population is expanding so rapidly that we need perpetually more new buildings, but because the buildings we already have are perpetually failing and need to be perpetually replaced. The industry does not profit from buildings that stand. It profits from buildings that fall. That is not a conspiracy theory. That is a straightforward reading of the business model, available in any industry analyst report, stated plainly in the financial logic of every publicly traded cement company's growth projections. The question is not whether this dynamic exists. The question is why it took so long for anyone to say it out loud. Ideas don't just die in the marketplace. They die in classrooms first. For Portland Cement to maintain its unchallenged dominance in the construction industry, it wasn't enough to simply manufacture and sell it at scale. It was necessary to establish, at the institutional level of engineering education, a narrative framework in which the Roman approach was understood as inferior, primitive, and superseded, rather than what the physical evidence actually suggests, which is that it was superior in several critical dimensions and poorly understood by the civilization that displaced it. That narrative was built methodically over generations through 2 primary mechanisms. First, engineering curriculum design. The foundational engineering programs that train 20th century construction professionals in the United States, the United Kingdom, across Europe, were built substantially around Portland cement as the assumed baseline material. Students learned its chemistry, its curing behavior, its compressive strengths, its workability, its reinforcement requirements. They learned to specify it, test it, and troubleshoot it. The curriculum was effectively written backward from the material the industry needed engineers to use. Roman concrete appeared, when it appeared at all, as a historical curiosity, discussed in the context of ancient engineering achievements, filed under what the Romans somehow managed to do without modern knowledge, and firmly categorized as belonging to a pre-scientific era that modern engineering had transcended. The implicit message embedded in this framing was clear: we have moved beyond this. We know better now. The 2017 Berkeley study revealed, with electron microscope precision, that this framing was backwards. Second, standards bodies and building codes. The ASTM international standards, which govern what materials are acceptable in U.S. construction and their equivalents worldwide, did not develop as purely neutral scientific documents. They developed in close collaboration with the industries whose products they were standardizing. Portland cement manufacturers participated in the standards process that defined what acceptable concrete meant. The standards they helped write specified Portland cement. The building codes written from those standards specified Portland cement. An architect or engineer who wanted to specify a Roman formula pozzolanic concrete for a modern project would find themselves immediately in conflict with the code. Not because the material fails structurally, the Mediterranean seafloor provides 2,000 years of third-party performance data, but because it hasn't been tested to ASTM standards, because those standards were not designed with it in mind, because the institutional gatekeeping mechanism that determines what is and isn't acceptable in modern construction was built by the people who profit from the answer being Portland cement. Pozzolanic concrete isn't rejected by the engineering establishment because it doesn't work. It's rejected because the paperwork hasn't been filed. And the people who would file the paperwork are the same people who would be filing it against their own financial interests. This is how knowledge gets buried without anyone issuing a burial order. No dramatic suppression, no shadowy committee, just the slow, structural accumulation of institutional incentives all pointing in the same direction, until the alternative becomes, in the professional vocabulary of the field, simply non-standard, which in practice means non-existent. The Pantheon doesn't appear in most structural engineering textbooks as a case study in material science. It appears as a photograph in the history chapter. And then the students turn the page. Let's be precise here, because precision is what separates knowledge from mythology. The Roman formula is not complicated. It is not exotic. It does not require rare earth elements, proprietary machinery, or industrial infrastructure. It requires three things that human beings have had access to for the entirety of recorded history, and one of them falls out of volcanoes for free. The core Roman marine concrete formula, as documented by Vitruvius and confirmed by modern spectroscopic analysis of surviving structures. Component 1, pozzolana, volcanic ash. 3 parts. The primary reactive ingredient. Roman engineers specifically prized the gray-brown ash from the Phlegraean fields near Pozzuoli, Italy, rich in silica, alumina, and the reactive aluminosilicate compounds that trigger tobermorite crystal formation when combined with lime and water. Vitruvius was explicit. Not all ash is equal. Volcanic ash from active or recently active geological zones is chemically distinct from wood ash or agricultural ash, and that distinction is everything. Component 2, hydrated lime, calcium hydroxide, 1 part. Not Portland cement, not modern quicklime, straight from an industrial kiln. Hydrated lime, calcium hydroxide produced by carefully adding water to burnt limestone, a process called slaking, which the Romans produced in open pits and aged for months before use. The aging process matters. Freshly slaked lime is chemically aggressive and less workable. Aged lime putty, allowed to mature over weeks or months, produces a smoother, more reactive paste that integrates more completely with the volcanic ash. Component 3, aggregate, variable. For land-based construction, the Romans used rock rubble, broken ceramic, gravel, and volcanic tuff, essentially the largest solid material available locally. For marine construction, they packed large chunks of volcanic rock, specifically tuff and lucite, into the wooden forms before pouring the ash-lime mixture around them. This aggregate is not structurally inert filler. In the marine formula, the mineral composition of the volcanic aggregate actively participates in the long-term crystal growth chemistry. Mixing ratio for practical land construction. 3 parts, volcanic ash, 1 part hydrated lime, aged minimum 2 to 4 weeks as lime putty. Water added gradually until the mixture reaches a thick, workable consistency, drier than modern concrete, closer to the texture of stiff clay. No steel reinforcement, no chemical accelerants, no admixtures. Pour it, pack it, leave it alone, and then wait. Because waiting is the most important part of the process, and it is the part that the modern construction industry structurally cannot afford to do. The honest geographical reality is that high-grade natural pozzolana, the specific volcanic ash Vitruvius described, is not universally accessible. Italy has it in abundance. Certain regions of Turkey, Greece, Germany, the Rhine Valley deposits of Trass, Ethiopia, and the western United States have workable natural pozzolanic deposits. Much of the rest of the world does not. But the underlying chemistry doesn't care about geography. It cares about reactive aluminosilicate compounds. And modern industrial processes produce several byproduct materials that contain exactly those compounds in sufficient concentrations to replicate the pozzolanic reaction with reasonable fidelity. Substitute 1, fly ash, class F. The most widely available pozzolanic substitute globally. Fly ash is the fine particulate byproduct captured from coal-fired power plant exhaust, an industrial waste material produced in enormous quantities that most developed countries currently pay to dispose of. Class F fly ash, produced from burning anthracite or bituminous coal, has a combined silica-alumina-iron oxide content exceeding 70%, sufficient reactive aluminosilicate chemistry to produce meaningful pozzolanic reactions with hydrated lime. Practical mixing ratio, substitute fly ash for volcanic ash at a 1.1 ratio by volume. Expect slightly different workability and color. Expect similar long-term durability performance, though the tobermorite crystal formation chemistry may differ in detail from the original Roman formula. Important caveat, Class C fly ash, produced from lignite or subbituminous coal, contains significant calcium oxide and behaves differently, more like a hydraulic cement than a true pozzolan. Use Class F specifically. Substitute 2, metakaolin produced by heating kaolin clay, the same material used in ceramics and paper production, to approximately 700 degrees, calcining it to drive off the chemically bound water and create a highly reactive amorphous aluminosilicate powder. Metakaolin is arguably the closest chemical analog to natural pozzolana available as a commercial product, with high silica and alumina content and excellent reactivity with hydrated lime. It is more expensive than fly ash, but more consistent in quality and more widely available than natural volcanic ash in non-volcanic regions. For serious pozzolanic construction applications, metakaolin is currently the premium substitute of choice among researchers working to revive Roman concrete techniques. Practical mixing ratio: 2.5 parts metakaolin to 1 part hydrated lime, slightly richer than the volcanic ash formula because metakaolin's particle geometry differs from volcanic ash and requires adjustment for equivalent reactivity. Substitute 3, ground granulated, blast furnace slag GGBS, a byproduct of iron production. The glassy granular material skimmed from blast furnaces and ground to a fine powder. Latently hydraulic rather than purely pozzolanic, GGBS activates slowly in the presence of lime and produces a dense, low permeability binder. Less dramatic long-term crystal growth than volcanic ash, but excellent resistance to sulfate and chloride attack. Good choice for foundations and below-grade applications. The honest performance hierarchy based on available research: natural volcanic pozzolana, original, metakaolin, Class F fly ash, GGBS, modern Portland cement substitutes. The economics of Roman concrete are so straightforward they almost seem like a trick. Modern Portland cement concrete: $50 to $120 per cubic meter for basic structural mix before labor. Before reinforcing steel, add $30 to $80 per cubic meter for rebar before the accelerated replacement costs built into its 50 to 100-year service life. Roman formula pozzolanic lime concrete: $8 to $15 per cubic meter for materials, depending on your region and which pozzolanic substitute you use. No steel reinforcement required for most applications. Service life measured in centuries, not decades. The material cost differential alone is 4 to 6 times cheaper at the point of initial construction. When you factor in life cycle costs, the repairs, the partial replacements, the eventual demolition and reconstruction that Portland cement structures require and Roman concrete structures do not, the economic gap becomes almost incomprehensible. A Roman formula wall built today should not need to be rebuilt within your lifetime, or your children's lifetimes, or your grandchildren's. Run that calculation across a family home, a structure that a modern family expects to significantly renovate every 20 to 30 years and fully replace within 2 to 3 generations. And you begin to understand what 2,000-year durability actually means in financial terms. It means one construction cost, ever. There is one genuine, non-negotiable disadvantage to Roman concrete, and it is important to state it plainly rather than pretend the formula is a perfect solution for all modern applications. Roman concrete is slow. Portland cement concrete achieves roughly 70% of its design strength within the first 28 days of curing. Fast enough to strip formwork, fast enough to load, fast enough to meet construction schedules measured in weeks and months. Roman formula pozzolanic concrete gains strength on a fundamentally different timeline. Initial workable hardness, days to weeks. Structural strength sufficient for loading, months. Full strength development, the beginning of meaningful tobermorite crystal growth, years to decades. The harbor walls that are still standing in the Mediterranean weren't strong enough to function as harbor walls the week they were poured. They became what they are across years of slow chemical development. The material that makes them extraordinary, the self-healing crystalline mechanism, the seawater-activated reinforcement, is the product of that slow timeline, not a feature separate from it. In a world where construction projects are scheduled in weeks, financed on quarterly reporting cycles, and evaluated on rapid delivery metrics, this is a genuine constraint. Roman concrete is structurally incompatible with the economic logic of modern commercial construction, not because it performs worse, but because it performs on a timescale that modern finance cannot accommodate. This is not an accident of chemistry. This is, in a very real sense, the final layer of the commercial barrier. Even if every engineer wanted to use the Roman formula, the investors financing construction projects operate on timelines measured in fiscal years, not geological ones. The material is too patient for the market, and a material that the market cannot finance cannot be built at scale, regardless of how superior it performs. For individual builders, however, for anyone constructing for their own long-term use rather than for rapid commercial return, this trade-off inverts completely. If you are building a home for yourself, for your children, for the generations that will carry your name after you, slowness is not a cost. It is the mechanism of permanence. Here is what nobody in the $400 billion cement industry wants you to walk away from this knowing: you can build with this formula today, legally, at a fraction of the cost of conventional construction. The recipe is not classified, it's in Vitruvius, freely available, translated into dozens of languages, sitting in public libraries. The materials are not controlled substances. Hydrated lime is sold at agricultural suppliers. Class F fly ash is available from industrial material brokers, often cheaply or freely as an industrial byproduct that facilities need to dispose of. Metakaolin is available through ceramic suppliers and specialty construction material distributors. The knowledge is not forbidden in the sense of being illegal. It is forbidden in the sense that nobody is financially motivated to teach it to you. Your contractor doesn't know it because his training didn't include it. Your architect doesn't specify it because the building codes weren't written around it. Your local hardware store doesn't stock lime putty in the quantities you'd need because there's no supply chain built for material whose adoption the industry has structurally discouraged for 200 years. The barrier is not a law. It is an absence of education, of supply chains, of cultural memory, and absences can be filled. Call it your Forbidden House vault, the structure that exists outside the planned obsolescence cycle, the building that your great-grandchildren will photograph as an architectural curiosity, not because it is exotic, but because it is simply, impossibly still standing in an era when everything around it has already been torn down and rebuilt 3 times. Think about what you are actually building when you construct a home. Most people think they are building shelter, a place to sleep, to eat, to protect their family from the weather, and they are. But they are also making a statement about time, about how long they expect their intentions to matter, how far into the future they are willing to project their presence on the earth. A Portland cement house says, "I'm building for my lifetime, perhaps my children's." After that, it's someone else's problem. A Roman concrete structure says something different. It says, "I built this for everyone who comes after me, including people I will never meet in a future I cannot imagine." It says that the quality of what I make today is worth more to me than the speed with which I can make it. It says that permanence is a form of generosity, a gift left for strangers across centuries. The Romans, who poured the Pantheon's dome in 125 AD, did not know that tourists from countries that didn't yet exist would stand beneath it in the year 2025, looking up through an oculus open to a Roman sky, in a building that has outlasted every empire, every plague, every war, and every competing architectural philosophy that history has produced. They just built it to last. That choice is still available to you. The recipe is written down. The materials exist. The only question is whether you are building for the next mortgage cycle or for the next millennium.